Thank you very much. Thanks for the invitation. Thanks for being here. We're shifting our attention now to the language system. And just to give you an idea, we only have 20 minutes this morning, so it's a bit short on time, but we haven't 25, that makes all the difference. But we have a YouTube channel, so you will see a little YouTube link on my slides, and if you see it, it means there's an entire dedicated talk about that particular slide available online. Now, I have the pleasure of talking about the neuroanatomy of language, and just a brief introduction to who I am and why I love language. I'm originally from Munich. Most of you know Munich for the Oktoberfest. That's not all we have. We also have a fantastic setup of different institutes. So the Oktoberfest is in the heart of the center, and around it we have Max Planck institutes and two famous universities. Now, this is where I learned my neuroanatomy using the brain, the actual brain. And then the link to language comes when you look at my trajectory in town. So I moved around. I lived in this part, moved to that part of town, moved across the river, realized it was nicer on the other side, so I moved back. Now, if we look at Munich overall, then really I had no other choice than study the neurobiology of language. And that's what I want to talk to you about today. So my own trajectory with the brain, as I said, started in Munich back in 2006, doing post-mortem Klingler dissections. And at that time, I became absolutely fascinated with the connection anatomy of the brain. And very lucky for me, tractography and I were born in the same year. So by the time I learned about the brain, tractography was ready to be applied. So I could combine the two methods and study the white matter ex vivo and in vivo. And here's a couple of examples where you can see how we cross-validated the methods using tractography and Klingler postmortem dissection in combination. And you can also see that back in 2011, just showing a tract was enough to get you into Nature Neuroscience. Nowadays, I'm afraid to tell you, you have to be a bit more clever than we were at the time and do more than just show a tract. Anyways, so I want to get us all on the same page before we begin. So here is a simple question to all of you, and we're not doing the fancy online thing, just raise your hand, please. And the question to you is, how many lobes does the brain have? So I say the numbers, you raise your hands. 1, 2, 3, as discussion is starting. 4, the first try attempts. 5. Well, the middle stretch is convinced it's 5. 6, 7. Anyone wants to go higher? Okay, that's a question I tend to ask many audiences, and the reply is always the same. There's a big discrepancy in the room, and people start to be quite unsure how many lobes the brain has. And that is partially due to the fact that our definition of lobes has changed over time. So for those of you who thought we have 4 lobes, I'm sorry to tell you, you're stuck in the 19th century. For those of you who thought it's 5, welcome to the 70s. And for those of you who thought it was 6, you're already in the 90s. Now, the definition of the lobes is still controversial. Some might argue there's even a 7th lobe, but time will tell how we divvy up the brain. In the clinical area, the lobar differentiation is not actually that helpful, but I thought, do you know what? Everyone is using AI. Let's ask our clever little friends how many lobes they think the brain has. So I started with Google, old school, in May, and Google thought it was 4. But I'm very persistent, so I just asked it again in September, and lo and behold, it updated. Someone must have published a paper, and now it thinks it's 6 lobes. But then ChatGPT came along, right? So you gotta ask ChatGPT what it thinks. Now, here is the thing. I asked ChatGPT over and over again, exactly the same question. And the first time it said 5, the second time it said 4, and the third time it said 6. So the take-home message here is just ask ChatGPT often enough, and you get the answer you want. But it's also for anatomy, it's probably not the best tool to use. Okay, so now we know the lobes. How about the white matter? how many... Nicola is already looking at me. How many white matter tracts does the brain have? Show of hand. 10? 20? 30? 40? 50? 60? 70? There's a few brave ones in the audience, but the general pattern is that you're all shy now. But you're right, it's a trick question, because we don't know. So here's a connectome of the human brain, and we can see that the white matter is rather continuous, and unless you know your anatomy and your way around, it's quite easy to get lost, even though smitten by the beautiful reconstruction of the white matter. But what you see here is the color coding. That is a classical RGB map, so red, green, and blue for the orientation of the white matter. But what you can also see is that separating individual bundles of fascicles can be quite difficult. And there's different schools where bundles get defined based on their trajectory, their main core, or their cortical projections. Now, that leads me to another point, which is that we have one brain, but we have many different anatomies in the brain. And that is because when you look at the surface of the brain, the gyra and the sulci, and we had a beautiful introduction just now before from Hiromasa, we label the brain in one way. If we cut through the brain, look at the sectional anatomy, you get a different labeling. If we look at the connections, it's different, and the functional anatomy. Now, what that means is that you can have different areas that have the same name or the same, sorry, the other way around. So you have multiple names for the same part of the brain. And then I personally work a lot with neurosurgeons, which makes it even more complicated because they flip everything upside down. Okay, now, knowing your way around anatomy, navigating neuroanatomy, it helps if you speak language. And just to give you one story, and I'm happy to talk about the less PC stories in the brain over a beer, but to give you one story is the temporal lobe. Any idea why the temporal lobe is called the temporal lobe? And what that has to do with George Clooney? I just heard it. I don't know where. Gray hair. There we go. Gray hair, exactly. So the idea is that this part of the hairline goes gray first, so it shows aging or the passing of time. Time, tempus in Latin, gave the name to the bone, and then the bone gave the name to that part of the brain. So there's many funny stories in the brain, some of which do not go on record, but you can hear them later if you like. Okay, when we look at the neurobiology of language, you probably at some point heard about our famous people, Paul Broca, who described a lesion in the inferior frontal gyrus associated with articulation, or a lesion in there with the lack of articulation, I should say. Then we have Karl, who also described a series of cases, but they had a lesion to the temporal lobe, and their language deficit was in comprehension, not in articulation. And then many years later, we had Norman Geschwind, who included the inferior parietal lobe as a concept area into the mix. Now you can see that the first model of language was proposed by Karl, surprisingly on the right hemisphere. And the pattern of connectivity has slightly shifted from a psychic arc going through the insula to the arcuate fasciculus, arcuate meaning arching, around the sylvian fissure. Now, if you put it all together, then our classical model of language in the brain looks a bit like this. Most textbooks you open, you have Broca's area, you have Wernicke's area, sometimes Geschwind's territory in the inferior parietal lobe, and they're interconnected by the arcuate fasciculus. Now I'm going to spend the rest of my talk to tell you why this model is wrong. Wow. Shocked faces. Okay, so first problem that we have is if you ask experts, so there's a society for the neurobiology of language, they polled their attendees and realized that when we're talking about Broca's area or Wernicke's area, we're not necessarily talking about the same thing. And this is from 2016. Didn't figure that out until then. So here is the percentages, how Broca's can be defined. So 44, 45, 49% say this is Broca's area. If you include 47, then 24% think that's Broca's area, and so on and so forth. You get the idea. Now, if we put it all together, then we see that we by no means have a majority for any of these regions. It's 49% for Broca's area and 26% for Wernicke's area. So the take-home message here is use anatomical labels, be specific which part of the brain we're actually talking about, because we're not necessarily talking about the same part. And this is people within the same field, let alone talking to people outside the field. So anatomical labels over eponyms. Now, the other thing is when we look at the dorsal and the ventral network, so all the white matter that is connecting those regions in the brain, we can see that the differentiation between dorsal and ventral networks is based on whether they arch around or below the Sylvian fissure, but really the cortical terminations, as you can see, are both below and above the Sylvian fissure. And that is for the dorsal network here, but we see the same thing for the ventral network. Okay, moving on to the next. Hiromasa already showed the next slide beautifully, but I'm going to show it to you again because I want to make a different point here, and that is that, yes, anatomy can be complicated, and for every box in these diagrams, you can imagine it's a cortical area, and every line is a white matter connection. And if we agree that systems like the visual system and the auditory systems are as complex as shown on these beautiful studies, then surely something as complicated as language has to have a better wiring diagram than this. Now, tractography has added to our wiring gram of language in the brain, but also electrophysiological studies, direct cortical stimulation in neurosurgery, and as you can see, we have expanded the language network, extended it, far beyond the classical arcuate fasciculus that was described in the 19th century as a fronto-temporal connection connecting inferior frontal gyrus, posterior temporal gyrus, so Broca's and Wernicke's, roughly. And then the early 2000s, Marco Catani added the indirect pathway that connects to the inferior parietal lobe, and since then, many more tracts have been associated with some function related to language in the brain. Another problem I have with this image is the following. So, any idea who these ladies are? Nobel Prizes. In fact, these are all the women that won the Nobel Prize for medicine or physiology. And I asked my student to come up with an average image of what you need to look like as a woman to win the Nobel Prize. Are you ready? Here we go. This is what you need to look like. Now, there's a couple of important things to take away here. The first one is the image in the middle doesn't look like any of the individual faces around it, nor does any of the individual faces around it look like the image in the middle. The second important take-home message is if you want to be in the average, check this out. Leopard print is what gets you in the average image. Comes from France. Here we go. Now, why this is a toy example and it's plain obvious when we look at faces, that's exactly what we do with our brain models, and it's a lot less obvious here. So here you have the average MNI template that you've all seen, and areas that are, where's my cursor? I lost it. Anyways, if you look at the basal ganglia, so the center of the brain, we can see that the boundaries are quite sharp, but as we go further away, so the temporal lobe, for example, that's the posterior end here, it becomes more blurry, and blurry means more variability in the template. Now, I'm going to show you two examples. You've already seen this paper in Hiromasa's talk, and he was right. The inverted omega sign is usually an anatomical landmark to identify the hand knob area, but you don't see that in every participant. In fact, it can be an inverted omega, it can be an epsilon sign, or it can even be a straight line in some people. So there's a huge degree of variability in the gray matter. This variability is exaggerated in the white matter. So here are two healthy students drawn from a sample in our institute. And if we look at the uncinate fasciculus, which is the teal connection between the the orbitofrontal and the anterior temporal lobe, you can see that in the top brain we barely can see it. In the bottom brain, it's a very prominent tract. Now, this is obviously hand-picked examples, but we looked at this on the group level. So here's the HCP data set where we looked at the variability in the gray and the white matter. And what you can see here is that there is a gradient of variability. And that gradient is in a way that the deeper parts of the brain tend to be more alike, and the lateral parts of the brain tend to be more variable. Now, this is a critical piece of information because that means if you use an atlas, the atlas will be somewhat accurate in the center of the brain. It will be a lot less accurate if you use an atlas to identify individual anatomy if you're outside the center of the brain. Now, this is obviously at the group level, and we were interested in individual tracts and what that means. And here is the work of my PhD student, Lilith Dulian, who will present a poster on this as well. And she dissected all the connections of the dorsal and the ventral networks for language and looked at the left and right asymmetry. Now, this in itself is another issue with the model because we only ever see the left side, but these tracts are all there in the right side, right? So that means they're bilateral with a slight preference for one side or the other, but functionally, it's not that we only have the language system in the left. The exact same anatomical system is present in the right, so there's a functional shift somewhere along the way. Now, what we can see is that some of these tracts tend to be strongly left lateralized, some of them are slightly left lateralized, and some of them are even right lateralized. Now, overall, the variability tends to be greater in the left hemisphere compared to the right hemisphere, and we were interested in which tracts exactly are the most variable. And when we look at them, we can see that the anterior segment of the arcuate fasciculus, the uncinate fasciculus, and the inferior frontooccipitalus are most variable in the left hemisphere. Now, another thing you can do with this data is, so far I've shown you healthy control data, but we can obviously look at patient data, and we have seen that accounting for the variability in anatomy actually helps us predict language outcome after stroke. And there's various studies that we published on a 6-month outcome and a 1-year prediction, but you can literally just take a data set and dissect all the white matter tracts and look at the patients who recovered and who did not recover, and look at the white matter if it was spared or if it was disconnected. So this is the work of Sabrina Beber and Chris Foulon, who are here as well, having a poster, and they looked at aphasic stroke patients who lost their ability to communicate, either because articulation or comprehension was impaired, and then looked at the anatomical correlates of their clinical deficits, and we can see that we can pick up segments of the arcuate fasciculus here. Now, this is quite a simple way to analyze your data. Nowadays, you can also throw in a lot more computational power, so we have a disconnectum symptom discoverer software, it's a website. You find it if you go to our lab's website, and you can just upload a lesion, and it will give you the pattern of disconnection for your group and also a prediction of the recovery. Okay, we're still not done. So I've shown you many arguments why I believe that this model is an oversimplification of how language works in the brain, but what I haven't touched upon yet is how language is extremely dynamic, right? We communicate at high speed, and not only do we use words and sentences, we also use gestures, facial expressions, we read the room, there are so many signals that we need to integrate. So we recently argued that this classical modular view on how the brain works is probably not sufficient to capture this complexity and dynamic shift in language in the brain. Neither is the hierarchical model, where you have the classical arcuate fasciculus connecting, and the idea is that for repetition, for example, information has to get in, it gets processed, it gets propagated to the frontal lobe and then repeated. But what we actually propose in this paper is that language is an emergent function of the brain that relies on the integration of different parts of the brain and networks in a dynamic fashion. Now, it took me a while to really conceptualize it and think about a good example, and the best example I can give you is that if you ask me where language is in the brain, it's akin to asking an orchestra where their music is. It's not in the individual instrument, it's not in the notes, it's not in the conductor, it's in all of them coming together in a timely manner and dynamically interacting. And this is how I think language works in the brain. Now, if you want to learn more and if you want to also try tractography for yourself, get those pretty pictures, go to the website, all the data is there, all the software is there, and on the YouTube channel you have all the tutorials to have a bit of fun and play around. Thank you.
Stephanie, lovely talk. Fantastic. The app kicked me out, so let me see. No questions in there yet. So while people are typing, I've got a question. You know, you said there's a greater variability in the lateral part of the brain than in the medial, or the hemisphere than in the medial part. Do you think that's associated with phylogeny, so older versus newer, or does it also have to do with the fact that the lateral fissure is the first one that appears in ontogeny, or is it a combination of both factors?
We actually looked at the evolution, and you can see that it maps onto the dual origin theory. It's exactly the same trajectory. So yes, there's an evolutionary component in the variability.
I'll definitely be asking you. You have a beer, I'll have something else. These other terms that you didn't want to talk about here, you know. Yes, here, question. I heard that some people have right hemisphere dominance in language. In them, white matter lateralization also flipped?
It's a very good question. So the right hemisphere dominance is mainly a functional dominance that we can see. Sometimes it's linked with a flip in the white matter, but not necessarily. So that's quite an interesting pattern. We also, in terms of classical confusions, we thought language and handedness should go together. But when we looked at it, we actually found that the arcuate fasciculus was not correlated with handedness, but it was the superior longitudinal fasciculus, so a frontoparietal network. So there are some surprises in anatomy still.
Is the lateralization of each tract of language network affected by different needs and experiences of each speaker? Like, so, you know, some people are bilinguals, others aren't?
Absolutely. So there is a couple of studies that looked at trying to dissociate genetic and environmental factors, and they found different patterns for different tracts. So the long segment, for example, seems to be more driven by genetics, whereas the posterior segment of the arcuate seems to be more driven by experiences. So acquiring literacy, learning to read and write, will change the volume of the posterior segment, for example.
Thank you. Thank you, everybody, so much for all of these really interesting questions. There's one more for you, because we've got time for another one. You suggested that the localization of language in the brain is not specific. Does phenotypes of lesions support this?
So it's not that it's not entirely specific. What I'm saying is it's not as specific as we think from functional imaging, for example. So you can run your localizer and get areas, but we have tons of clinical data that suggests that the picture is a lot more complicated, because you can have a lesion in the inferior frontal gyrus but not present with a classical Broca's-like aphasia. Likewise, you can have a lesion elsewhere in the brain and not and present with Broca's-like aphasia. So the clinical data suggests that the story of language in the brain is a lot more complicated than two areas connected by one tract.
Okay, and a final question. Does variability increase over development, and is it linked to behavior like reading and language acquisition?
Brilliant question. So yes, as I said, variability changes with, the track changes with the acquisition of literacy, so there will be more variability based on experience. And in terms of the developmental tract of variability, that's something I'm currently looking at with Kurt Schilling. So stay tuned for the results.
Wonderful, thank you very much.